Greetings, it's Paul Bamberg with the introductory video for Class 23 of Math 117. This involves some very messy algebra and calculus, but I hope it will give you an overview of how one derives the Black-Scholes differential equation and checks that the Black-Scholes formula is a solution to it. So let's get going. Our criterion for the fair pricing of call options is that the fair price has to be a martingale, and we can implement that idea in the binomial model. We can say in the binomial model the price evolves over steps, each of which has a length delta t, and in one step the price either gets multiplied by u or it gets multiplied by a quantity d which is less than 1. And at the end of that time interval, depending on whether the share price went up or down, the call option will evolve either to a higher value, which I'll call V plus, or a lower value, which I'll call V minus. And the martingale condition is that the fair price at the start of this interval is the discounted value of the probability of an up step times the increased value plus the probability of a downward step multiplied by the decreased value. And P is the risk-neutral probability for the share price to rise, which we can work out from our binomial model. In fact, we have a formula from a month or so ago for the probability that the price will go up and the probability that the price will go down. I should say this is not how Black and Scholes derived this differential equation to start with. They started with a model that involves hedging, which we will do later. Deneen sort of mixes the two things up, but I've decided to try to do this purely on the basis of the binomial model. Now let's think of the value of the call option as a function. At any time, it depends on what time it is. That tells us how long is left to maturity, and on the price of the underlying shares, which I will denote by little s rather than capital S. We actually have a formula for this value. Now, if I set the share price equal to what we've been calling x sub t, the random variable that gives the share price at time t, and if I remember that at that time, the time remaining until the maturity date is capital T minus little t, then I can plug in capital T minus little t wherever we had capital T in the original formula. I can write S wherever we had V sub t. This formula has to be split over 2 lines, it's so long, but there is the Black-Scholes option pricing formula, explicitly written as a function of the time t and the share price little s at that time. Now let's think about what happens over a single step. This is the tricky part of the derivation because we have to keep all the terms that are important in the limit where delta t goes to 0 and not keep any other terms. It's messy enough without them. So recall that a step takes place between time t and a slightly later time t plus delta t, and delta t has to equal the square of delta x, where delta x determines by what amount the exponent might go up or down. To be precise, the binomial model will change the price from s either to a higher price, where we multiply the expectation by the exponential of mu delta t plus sigma delta x, or to a lower price, where we're taking the exponential of mu delta t minus sigma delta x. For short times delta t, I can approximate the exponential of mu delta t by 2 terms in the Taylor expansion. For the exponential of plus or minus sigma delta x, I have to keep 3 terms because delta x squared is going to be equal to delta t, so this is just first order in delta t. And we conclude that the share price goes up by an amount that involves the mu delta t and the sigma squared over 2 delta t with a plus sigma delta s, or gets changed by something. We've got a minus sign on the second term, which makes the price go down. Now, trying to stick with the notation from Deneen, I'm going to take mu plus sigma squared over 2 and replace it by c, so I have a slightly simpler notation for this. Now I need a Taylor series in 2 variables. So if I want to approximate the value of the option at time t plus delta t and share price s plus delta s, I have one term involving delta t, and I'm using v sub 1 to denote the partial derivative of the function v with respect to its first argument, partial of v with respect to t, if you like. The subscript 2 denotes partial of v with respect to s, partial derivative with respect to the second argument, and there I have to keep one more term because delta s squared involves delta x squared, and delta x squared is just equal to delta t. So this is the minimum number of terms in the Taylor expansion if we want to be able to work in the limit where delta t approaches 0. In fact, if I work out delta s squared, it is s squared. Where did delta s go? There it is. It's got an s squared in either case, and in either case we are going to have a c squared delta t squared, which we don't need to keep, and a term involving the product of these two terms, which we don't need to keep, and a term involving sigma squared delta x squared, which we replaced by sigma squared delta t. So now I've got everything written in terms of delta t and delta s. The Taylor expansion is the value of the function when both the increments are 0, a term involving the first partial with respect to t, a term involving the first partial with respect to x, and one more slightly unexpected term involving the second partial of v with respect to the share price s multiplied by delta t. Let's see what we can do with this. We say the initial share price multiplied by the factor that we get by putting money in an interest-bearing bank account has to equal the probability of an upward price times the higher price plus the probability of a lower price times that lower price. If the time interval delta t is short, I can approximate this exponential by 1 plus r delta t. Now, I also have just worked out an expression for v at time t plus delta t with share price s plus delta s, and that lets me work out what v plus is and what v minus is. V plus just involves what happens when s goes up, and v minus just involves what happens when s goes down. So there are the appropriate formulas for delta s plus and delta s minus. Thank goodness we're almost done. We substitute v plus and v minus into the fair pricing equation, and I'm not going to go back and check all the algebra in detail. The terms that have the same sign for price going up or price going down, not surprisingly, just get multiplied by 1, the sum of the probabilities. The term that has a different sign is the one involving delta s, and the expectation of delta s is the same as if the share had been deposited in the bank. In other words, p times the change when we go up plus 1 minus p times the change when we go down is equal to the interest rate times s delta t. I take the equation from the last page, I subtract v0 from both sides, that gets rid of the 1, in the 1 plus. Every term involves delta t. I divide through by delta t, and we get, in the notation of Dineen's equation, 11.33. R times the share price as a function of R times the option price as a function of time and share price is equal to the first derivative of that quantity with respect to time plus Rs times the partial derivative with respect to the share price plus sigma squared over 2 times the square of the share price times the second partial derivative of the option price with respect to time. This is the infamous Black-Scholes differential equation, and what Black and Scholes did was to derive this on the basis of hedging considerations, and then, remarkably, they were able to solve it to get their famous formula. That's quite a different approach from the binomial model approach that we have been using. So, we have a differential equation that is satisfied by the value of the option, and we also have a formula for it. Here's the Black-Scholes formula from the previous class, and now I'm going to switch over to the notation that Dineen uses starting on page 267 of the edition that I've got. We'll consider the value of the option at any time t that's in between 0 and the maturity time, capital T. Instead of writing capital X sub t, the value of the random variable x at time little t, I will just use the symbol x, and I will define a couple of functions, g and h. G comes from the first term in the formula. It's the log of x over k plus r plus sigma squared over 2 times, and now I have to replace capital T for an interval which started at 0 with capital T minus little t for an interval that starts at t. In the denominator, similarly, I have to replace capital T by capital T minus little t. If I look at the second term, I see that the only thing that's different is that the sigma squared over 2 has a different sign. So h is the function g minus the quotient of this term by that term, which works out to sigma times the square root of capital T minus little t. Now I can write the Black-Scholes formula, which Dineen is now symbolizing by u rather than v, so I'll do the same, as x times the normal distribution function applied to g minus the discounted strike price times the normal distribution function applied to h. And what we want to verify is that this function satisfies the Black-Scholes differential equation. Well, the first thing we have to do is find the partial derivatives of g and h. Here is the formula for g. Here is the formula for h, which is only a little bit messier. When you take the partial derivative of g with respect to its first argument, which is t, you notice that a t shows up there, and a t shows up there, and that's why we end up with two terms. When I take the partial derivative of h, I get the same thing that I got from g, but there's an extra term resulting from differentiating this with respect to little t. Taking the partial derivative with respect to the second argument, x, is quite a bit easier because the only place that x shows up is there. So from differentiating that logarithm, I am going to get a 1 over x, and then the sigma times the square root of capital T minus little t shows up in the denominator. Now we've got this normal distribution function. The derivative of that normal distribution function is the normal density function for which we have a nice neat formula. 1 over root 2 pi times e to the minus x squared over 2. And a calculation that's so messy that I'm not going to repeat it here shows that there's a simple connection between the normal density function applied to g and the normal density function applied to h. Here's our Black-Scholes formula again. U of t and x split into two terms involves x times the normal distribution function applied to g minus the discounted strike price times the normal distribution function applied to h. When I take the partial derivative of this function u with respect to its first argument t, the chain rule calls for me to differentiate capital N, which I'm quite happy to do because the derivative of capital N is just little n, for which I have a formula. And therefore, when I scrupulously apply the chain rule and then simplify by writing things in terms of little n, I get something that is not nearly as bad as it was before. Fits nicely on one line. Similarly, when I take the partial derivative with respect to x, x is sitting inside the argument of capital N, so I will get one term from the chain rule where capital N stays around, another term, and in fact a third term where I differentiate n. So there is the messiest of the three formulas. And when I take two partial derivatives with respect to the second argument, I have to differentiate the capital N in the first term, and I get a little n. Trust me, if you substitute all these partial derivatives into the original equation, it checks. If I take all these results and shove them in here, the right-hand side and the left-hand side are equal. We'll go over some of the more interesting details of this calculation in class, but I hope that will at least give you an overview of what's going on.